Hello everybody, welcome back. This week is all about thermal stresses and strain, thermal deformation. Before we move forward, I want to remind everybody with an engineering degree from outside of the United States, if you are interested in evaluating your education in this country, I have put together a PDF guide with step-by-step instructions on how to do that. Just click the link below and you'll be able to download it for free. Now let's move on with our problem. A steel rod of diameter 20 millimeters is fixed at the end as shown. At a temperature of 20 degrees Celsius, a gap of 0.1 millimeter exists between the right end of the rod and a rigid wall. If the temperature of the rod is raised to 120 degrees Celsius, what is the stress in the rod? So this is our rod, and here it is fixed at this wall, and we have a gap of 0.1 millimeters at the other end. The problem says if the temperature is raised to 120 degrees Celsius, what is the stress in the rod? Let's see, what is the stress? Stress equals to force over area. Due to the raised temperature, we are going to have a thermal deformation. Let's look in the FE handbook and find the formula for the thermal deformation. So thermal deformation equals to temperature coefficient of expansion. This coefficient, you can find it at the end of mechanics of material section. You have a table for it. L is the length of the member. T is final temperature, subtract initial temperature. Let's apply this formula and see what's happening. Let's go and see how much is alpha. We have a steel rod, and let's go ahead and look for it. We're going to go down at the end of this section, mechanics of materials. They provide you with a table where you can find these coefficients. Here is the coefficient of thermal expansion. And in our case, it is 11.7 times 10 to minus 6 degrees Celsius. So we have 11.7 times 10 to minus 6 degrees Celsius. Times the length of the rod is 130 millimeters. Times T, 120 degrees Celsius minus 20 degrees Celsius equals to 120 minus 20 will have 100 times 130 times 11.7 divided by 1 million. The thermal deformation, it is 0.152 millimeters. So the thermal deformation is 0.152 millimeters, meaning if the wall wasn't here, this rod will elongate 0.152 millimeters going towards the right. Now, this wall being here, the rod will only be able to deformate or to elongate 0.1 millimeters. So once the rod hits the walls will act on the rod as a compressive force, and we will have a deformation in the opposite direction. So let's see what is the deformation due to the compressive force. So deformation due to compression equals to, if you remember the formula, let's go back to the mechanics of material. Here we go. Uniax loading and deformation. This is the stress that we have to calculate, and here is the deformation due to load. Let's write this formula down. We have PL over AE. Okay, let's see. So we'll have the load P, which is the walls acting as a compression load on the rod. L, let's talk about the L. The length of the rod, once it reaches the wall, it's going to be 130 millimeters plus 0.1 millimeters. So the total length of the rod at that point, it's going to be 130.1 millimeters. And I think we have to transform this into meters because the modulus of elasticity usually is given in meters. So let's transform 130.1 millimeters into meters. You just divide it by 1,000. So you get 0.1301. 0.1301 meters. The area is the cross-section area of the rod, but I will write it for now as a symbol. I'll tell you why a little bit later. And let's see the modulus of elasticity for steel. We have to go again at the table at the end of this section and get the value for our modulus of elasticity. For steel is 200 GPa. We have 200 gigapascals, which is 10 to 9 pascals. And you know pascals is Newton over meter squared. If you don't know that, make sure to go to the unit section of the FE handbook. Okay, so giving these two equations here, let's talk again about what's happening with the rod so we can finish our equation. So the rod will deformate until it reaches the wall due to thermal deformation, due to the temperature. And once it reaches the wall, deformation will occur in the opposite direction due to the walls acting on the rod as a compression load. And after all this deformation occurs, deformation equals to 0.1 millimeters. So let's write it down. Deformation due to the temperature acting on the rod. Once it reaches the wall, we'll have a deformation going in the opposite direction due to the compressive load. And all this, finally, the final deformation that occurs is 0.1 millimeters. So all this is equal to 1 millimeters. So we'll have thermal deformation minus 0.1 millimeters equals to deformation due to compressive load. Thermal deformation equals to 0.152 millimeters minus 0.1. We have 0.052 millimeters, and let's transform that into meters. We'll have 0.52 meters times 10 to minus 4 equals. Okay, so we'll have 0.52 or 10 to minus 4 equals to P over A times, let's do the calculations up there. We have 6.505 times 10 minus 13. From here, we can calculate P over A, which is the stress that the problem is asking us to calculate. So we can do P over A, which is equal to the stress we have to calculate, and equals to 0.52 times 10 to minus 4 over 6.505 times 10 minus 13 equals to getting 79 938,508.8, and this is in newtons per meter squared. And let's make this result a little bit easier. And the answers are given in megapascals. So let's transform this in megapascals. Mega means 10 to 6, so we just have to move this comma 6 units in front. So we're going to get approximately 79.9. I'll just do 80 megapascals. This is our answer. And let's see which one it is from here. And it is C. That's it for today. I hope you found this video helpful. As always, I want to encourage you to subscribe and give it a like, because this helps people like you find me. Also, I want to remind everyone with an engineering degree from outside of the United States, if you are interested in starting the process and evaluating your education in this country, but if you don't know where to start, I have put together a PDF guide with step-by-step instructions on how to do that. Click the link below and you'll be able to download it for free. Keep on practicing a few problems, and I will see you next week.